Hello everybody, welcome back to Physics 425. So what I want to do to start is just to give kind of a overall summary of some of the things that we've learned about superfluidity so far, and in particular some of the conditions that are required for superfluidity to exist. So what we need to do is to first cool a system of identical bosons below the Bose-Einstein condensation temperature. And so just because you have a Bose-Einstein condensation does not necessarily mean that you will have superfluidity. So when we do have a Bose-Einstein condensate, what we find is that we have a macroscopic number of particles in the ground state. Another way that we had to look at this is to consider the so-called quantum volume, which we labeled as lambda d cubed. And so this is like the Debye wavelength of the particle, so how much space the wave function of the particle occupies. And so when the quantum volume occupied by each particle exceeds the available space per particle, let's say available volume per particle, which is given by V divided by N, which is 1 over the number density, then what we have in that case is that the wave functions of neighboring particles overlap. So particle wave functions overlap. And then what we attempt to do is to describe the entire condensate, which can be made up of a huge number of particles, using a single macroscopic wave function. Okay, and so that wave function has some amplitude and some phase. One thing that we found is that if we do have superfluidity, then the volume of the velocity of the superfluid is given by the gradient of the phase of this wave function. And so this phase is a smoothly varying function of position. We argued that a sudden change in the superfluid velocity would result in a sudden change in this phase of the wave function, which in turn would affect the velocities of all the other particles in the condensate. So it would result ultimately in a sudden change in velocities of a macroscopic number of particles. And so this is an unlikely event. Okay, and then one of the last things that we talked about was this critical velocity for superfluidity. And what we found was that superfluid flow, so flow without dissipation, is destroyed above a critical velocity v critical. And so we calculated this critical velocity for a few different cases. For a system of non-interacting bosons, where the energy is only the kinetic energy, h bar squared k squared over 2m, what we found is that this critical velocity is actually 0, which means that for any flow, superfluidity would be destroyed, and so that means you'd never have flow without dissipation. So for a system of free particles with only kinetic energy, we found that V critical was equal to 0, and so we get no superfluidity for a non-interacting system of bosons. And so maybe that's not an intuitive result. It's maybe even a little bit surprising. So in fact, interactions are necessary for superfluid flow. And so the other cases we looked at were a dispersion relation, energy versus momentum, or energy versus k, that was linear, and then one that was quadratic, but not quadratic centered on 0, but offset from 0. And these corresponded to the phonon dispersion for the linear case and the so-called roton dispersion for the offset quadratic case. And what we actually found is that the limiting critical velocity is actually the roton critical velocity for a system like helium-4. Okay, so what we want to do today is examine some properties of the so-called two-fluid model. And in fact, what we're going to do is we're going to focus on the fraction of particles that are belonging to the superfluid. And so just for your own reference, these notes are based on chapter 2 of a book written by Tilley and Tilley. So if you look up the authors Tilley and Tilley for a low temperature physics book, and you'll find it, and chapter 2 is what the following notes are based on. We start by postulating that the condensate, or the superfluid fraction, is governed by a single wave function. And so that's a concept we've been talking about a little bit already. And so here's our wave function. It's going to have an amplitude. This time we'll let the amplitude possibly depend on position. And then it has an e to the is, where s is this phase factor. We'll assume that the wave function is a solution to the time-dependent Schrodinger equation. Okay, and so the Schrodinger equation is IH bar times a time derivative of the wave function, and so this is our energy, is equal to minus h bar squared over 2m, and so we'll put an m4 because we're talking about helium atoms, and then it's two spatial derivatives, which we'll write as del squared of the wave function. This is the kinetic energy, and then there's a potential energy term. So potential energy. Okay, so before we get too much into the calculation, let's see if we can come up with some interpretation of the different parts of the wave function. So interpretation of the wave function. Well, we've already seen what the phase represents. So we already saw that the gradient of the phase describes the superfluid velocity. And so just to recap, that superfluid velocity was h bar over m times the gradient of the phase. So the next question is, well, what about the amplitude? And so we call that phi 0 above here. So phi 0 is the amplitude of our wave function. It's the prefactor in front of the exponential. What we're going to find out is that we're going to be able to relate this amplitude to the density of the superfluid particles as a function of position and time. So how are we going to do that? Let's think of a more familiar case to start with. And so let's think of a single particle. So we write down a wave function for a single particle. This could be, for example, the electron that surrounds the nucleus of a hydrogen atom. So an electron going around a proton. So for a single particle wave function, so our example we might keep in mind is the electron in a hydrogen atom. When we take the absolute square, what it tells us is the probability density of finding the particle, or the electron in our case, at a position r. Okay, so these wave functions are position dependent, and so the square of the wave function tells us this probability density. If we now have an extremely large number of particles, with the same wave function, which is the case we're considering in our Bose-Einstein condensate of helium atoms. And we look in any volume in Cartesian coordinates dx, dy, dz, for example, then the number of particles is expected, the number of particles expected in that volume is proportional to the absolute square of the wave function times this volume element. So if you did this for a single particle, like the electron in the hydrogen atom, then the square of the wave function times the volume element tells you the probability of finding that one particle there. But now if you have tons of particles, all described by the same wave function, then they all have the same probability of being in this little volume, and so the number of particles you expect there is just proportional to this probability and to the number of particles that the wave function describes. So therefore, when we have an enormous or macroscopic number of particles with the same wave function, then the square of the wave function can be used to describe the density of particles. So the square of the wave function times a volume element is proportional to the number of particles inside that volume element. If we divide by the volume element now, then we get the density of the particles at some position r. So what we could do is we have some choice in our normalization constant, and so we're going to choose the normalization of our wave function such that the square of the wave function is equal to the average number of superfluid atoms per unit volume, or the superfluid density. So the conventional choice is that the square of this wave function, and because we've chosen to write the wave function as an amplitude times a phase, when you multiply the wave function by its complex conjugate, the phase factor vanishes, and we have only the square of the amplitude. And so phi 0 is a real number, so we just square it instead of writing the absolute square. And we're going to say that's equal to the superfluid density divided by the mass of helium atom. So rho s is the mass density of the superfluid particles, and rho s divided by m4 is the number density of superfluid particles. Okay, so next, what we're going to do is we're going to try to go through an argument to see if we can figure out what we should write for the potential energy in our Schrodinger's equation, right? So if we go back to the time-dependent Schrodinger's equation, we have the total energy, we have the kinetic energy, and we have the potential energy, but right now we don't have any sense of what the form of this potential energy should be. And so we're going to try to work through a bit of an argument to see if we can uncover something about what that potential energy looks like. So we do this by considering a volume of superfluid at rest. Okay, so this volume has no kinetic energy. All right, so by the first law of thermodynamics, the change in sorry, let's not do the okay. Yeah, that's fine. The change in internal energy of the system is described by, well, we've used this many times. I'm going to put a subscript 0 on here just to remind ourselves that this is going to be used to describe the superfluid at rest. So the 0 means at rest. So it's TdS, which is the heat, minus P dV, which is the mechanical work, plus mu dN, which is the chemical work. And so what we can do is we can manipulate this and we can say, well, that means we could write the chemical potential as du0 dn if we had constant volume and constant entropy. Okay, so now let's think about a superfluid that's now moving. So for a moving superfluid, we have to think about kinetic energy. So we must add kinetic energy let's say USK. So US is for some energy associated with the superfluid, and K is for the kinetic energy. To get the total system energy. Okay, so U total is going to be US kinetic plus U0, the internal energy for a superfluid at rest. Okay, and so maybe the picture is we have some superfluid maybe moving through a tube or something like that, and what we're going to imagine is a little spherical volume, and we'll say this is, say, position A, and maybe there's delta n particles in that spherical volume, and then that little volume of superfluid makes its way over to position B, and there's delta n particles in there. So we imagine moving a volume of superfluid with delta n particles from position A to position B. And so we can make note of a few things right away. If this is a fixed volume, then delta V is equal to 0. And our superfluid has no entropy. We saw that experimentally the superfluid carries no heat because it was going to flow from a cold region to a hot region. And so it can't carry any heat because that would violate another law of thermodynamics. And so dq is TdS, and so if dq is 0, then ds is 0. So it has no entropy, ds is equal to 0. The other thing we can say is that the flow of the superfluid involves no dissipation. And so there's no energy lost, and that means the total internal energy, or the change in the total energy, should be 0. Okay, so what we want to do is we want to go back and use some of these results. So in particular, the change in total internal energy is going to be overall 0, and it's going to be equal to the change in kinetic energy plus the change in this internal energy for the superfluid at rest. And we can calculate the change in internal energy at rest because we've identified that ds is 0, dv is 0, so the change in internal energy when the superfluid is at rest is just the chemical potential, which we've written here, times dn. Okay, so that's how we'll start. So when we remove delta n particles from the volume A delta U0, let's say A, is equal to minus du0 dn at constant entropy and volume delta n, and so this is all for, the notation's a little weird here, but let's say this is for position A. There's a negative sign because we've moved particles out of that volume, so we've lost energy in that little section. Then we're going to add delta n particles to B, and delta U0B is going to be equal to plus. It has the same form, except this is going to be for volume B, delta n. Okay, so now delta U, the total change in internal energy, we said had to be 0, and that has to be equal to the change in kinetic energy of the superfluid plus the change in the internal energy when the fluid's at rest and then we had a times delta n. So we moved delta n particles out of volume A and into volume B. Okay, but du0 dn at constant V and S is just the chemical potential. And so this is the chemical potential at B, and this is the chemical potential at A. And so what our conservation of energy expression looks like is the following. The total change in energy is 0, and that's equal to the change in the kinetic energy, plus now what we have is mu B minus mu A times delta n. And so if the total energy has a kinetic part, and so here's the change in kinetic energy, and a potential energy, then this must be the change in potential energy. So what we've argued now is that this difference in chemical potential times the number of particles involved is the change in potential energy of delta n particles, or let's just say helium-4 atoms. And so that means if we divide by this delta n, we would have the change in potential energy per particle, or the chemical potential is the potential energy per particle. And so mu is the potential energy per particle of the superfluid. And so with that, our time-dependent Schrodinger equation becomes IH bar d phi dt is the energy minus h bar squared over 2m4 del squared phi is the kinetic energy plus the potential energy times the wave function again. And so what we've done is we've done two things now. We've identified that the square of the amplitude of the wave function is the number density of superfluid particles at position R. We already know that the gradient of the phase of the wave function is the superfluid velocity, and now we see that the chemical potential is the potential energy per particle of the superfluid. All right, and so now we're just going to get into actually subbing our wave function into this expression and just working through the derivatives and to see where that leads us. So we're going to sub phi is equal to phi 0 e to the is into the Schrodinger equation, which is in the red box above. And we're going to allow that the amplitude of the wave function is a function of r and t, and the phase of the wave function is a function also of r and t. A couple things we'll make use of. We'll make use of a couple of identities with this del operator. Del squared is just del dot del. And the divergence of a coefficient a times a vector a is equivalent to the dot product of a and the gradient of the scalar a plus the scalar a times the divergence of vector a. So let's just keep those two in mind because we will make use of them. Okay, so I can't keep all this on the screen. There's the Schrodinger equation in the red box, and we're just going to sub our wave function into there. And I think we'll try to do this slowly. So the first part of Schrodinger is IH bar d by dt, and then our wave function is phi 0 e to the is. And that's equal to minus h bar squared over 2m4. And then it was del squared phi, so let's write del squared as del dot del, so this is going to be acting now on the wave function. And then it's plus our potential energy term, which is mu times the wave function, which is mu naught e to the is. Okay, so what we have to do is we have to do a whole lot of product rule and things like that. Okay, so we're going to get IH bar d phi 0 dt e to the is plus IH bar. And so we take the time derivative of e to the is. Now we have to do chain rule, so we get I ds dt phi 0 e to the is. Okay, so that's the left-hand side of Schrodinger's equation, and that's going to be equal to minus h bar squared over 2m4. We won't do anything with this first divergence yet, but we will act with the gradient operator on our wave function, and we have to do product rule again, so we would get the gradient of phi 0 times e to the is plus, let's see, I gradient of s, and then we just get the full wave function back again, phi 0 e to the is. And then we still have mu phi 0 e to the is. Okay, good. So we'll just keep working on the right-hand side of this equation. So what we have to do now is this divergence. So we have minus h bar squared over 2m4. Okay, so we have del dot del, and so I'll write the e to the is, and del dot del becomes del squared phi 0 plus. So we have to do chain rule, so we're going to get an I coming down from the exponential, then we'll have the gradient of phi 0 dotted with the gradient of s, and then we'll have e to the is. Still, let's see, plus I phi 0 e to the is. Then we have del dot del s, which is del squared s, plus by chain rule, by product rule, we're going to have plus I gradient of s dot gradient of phi 0 e to the is. So we're going to have to do a chain rule, a product rule again, but first let's close this bracket, and we still have the chemical potential times the wave function. Okay, so we're getting there. We still have the left-hand side is still the time derivative part over here, so we're still just working on the right-hand side now. Minus h bar squared over 2m4. So a lot of this stuff will leave the same. E to the is del squared phi 0 plus I. Let me reorder some of this. I e to the is gradient of phi 0 dotted with the gradient of s plus I phi 0 e to the is del squared s plus I gradient of s dotted with, and so here's where we have to do our product rule again, e to the is gradient of phi 0 plus I gradient of s phi 0 e to the is bracket bracket and chemical potential times wave function. Okay, so let's just write out the whole thing again. So we have the left-hand side, which involved the time derivatives. So that should be equivalent. The reason we get minus h bar is because we had a I times I over here. And so we turned that into a minus 1. Okay, and then that is all equal to minus h bar squared over 2m4. And we'll just write out a lot of these terms. E to the is del squared phi 0 plus I e to the is gradient of phi 0 dot with the gradient of s plus I phi 0 e to the is del squared s plus. Okay, so now here's where we're going to distribute this term a little bit. So we're going to get a, let's see, I e to the is gradient of s dotted with the gradient of phi 0. And then we have a I times I, so we're going to get a minus. And then we have gradient of s dotted with the gradient of s, and so that's the gradient of s squared. And then we have phi 0 e to the is, close the bracket, plus mu phi naught e to the is. Okay, so I think if we look at this, there's just a slight simplification. These two terms underlined in red are the same, just the dot product is written in the opposite order, but that doesn't matter. So what we'll do is we'll collect those terms, and at the same time we'll divide by the wave function, phi 0 e to the is. So if we do that, then the left-hand side becomes IH bar. We divide by e to the is, so that's gone. But we have 1 over phi 0 and then we have d phi 0 dt. Then we have minus h bar, and we're dividing by the wave function, so all that's left is the ds dt. And then we have the right-hand side, h bar squared over 2m. Okay, and so we're dividing by the wave function. So what we get is del squared phi 0 over phi 0. The exponential cancels. And then we have, let's just keep track of the terms that we've dealt with. We've dealt with that first term. I'm going to deal with this one next. We're dividing by the wave function so that all that remains is minus the gradient of s squared. Okay, now we'll think about these two terms together, I think. And so let's see, the exponential is going to cancel. We'll have a 2 because we have two of these terms. There's an I, and then there's the gradient of phi 0 dotted with the gradient of s. And then we still have the amplitude of the wave function that we divide by. Okay, and so that leaves only one more term inside these brackets here. The wave function part cancels, and we just have I del squared s. And so we end up with a plus I del squared s. And finally, let's not forget the fact that we have the chemical potential times the wave function, but we're dividing by the wave function. So we just get a plus mu. Okay, so what we have here is an equation that has some terms that are real and some terms that are imaginary. So this really represents two equations. So there's the real and imaginary parts. We're going to look at these two parts of the equation separately. To finish off today, we'll do some manipulation of the real part, and then the first thing I think we'll do in the next video is examine the imaginary part. And so let's just identify, say, the real terms. So here on the left-hand side is the real term. This is real, and this is real, and this is real. And then we have imaginary terms. So there's an I out front of the d phi dt, and there's these two imaginary terms on the right-hand side. Okay, so let's collect the real parts, and so we'll examine the real parts of this equation. So the real part is minus h bar ds dt is equal to minus h bar squared over 2m4, and then we have del squared phi 0 over phi 0 minus the gradient of s squared plus the chemical potential. Okay, so we can do a couple things. Let's multiply by overall negative sign, so then we'd have h bar ds dt is equal to, let's distribute the h bar squared over 2m, so we'd have h bar squared over 2m4 del squared phi 0 over phi 0 minus h bar squared over 2m4, the gradient of s squared. And then because we multiplied by overall negative sign, we'd have minus the chemical potential. Okay, we can do a little bit here. We know something about the gradient of S. So using the fact that the superfluid velocity is m4 over h bar times the gradient of S, what we could do is we could write that the gradient of S is equal to h bar over m4 times Vs. I think, is that going to be... I think I've got that backwards in my notes. Let's just go back and let's go all the way, check back here. We started with a summary here where, yeah, the superfluid velocity is h bar over m times the gradient of S. So I think I wrote that the wrong way. H bar over m times the gradient of S. So let's fix that. So Vs is h bar over m times the gradient of S. So that means the gradient of S is m over h bar times the superfluid velocity. The other change we'll make is that we know that the amplitude squared was the number density of the superfluid particles, and so that's the mass density divided by the mass. And so that means if we have just a single power of phi 0, which is some real number, the amplitude of our wave function, that we could write as the square root of rho over m. Okay, so if we do some of that, let's see, on the left-hand side, nothing happens. We have h bar ds dt is equal to, let's see, h bar squared over 2 m4 and then we have del squared phi 0. So phi 0 is rho over m4 square root, but then we're dividing by phi 0. So the 1 over root m factors are going to cancel, and we could write this as del squared, the square root of rho s divided by the square root of rho s, minus the gradient of s squared is going to be m squared divided by h bar squared. So there's going to be some cancellations. The h bar squareds are going to cancel, and we're going to get a 1/2 m4 left over. And then we're going to have Vs squared, which is Vs dot Vs, which is just the magnitude squared of the superfluid velocity. And then we have minus the chemical potential. Okay, good. So we're getting very close to where we want to be. So the last thing that I'll say is that in many circumstances, the superfluid density, rho s, is uniform, such that this gradient of the square root of the superfluid density is small. You know, in fact, when we were first thinking about interpreting the phase of our wave function, we started out by assuming that the amplitude of the wave function was independent of position. And so that's equivalent to saying that the superfluid density is uniform in position. Okay, and so if we do that, then we can ignore this first term on the right-hand side, and what we end up with is an equation that I'm going to identify as equation star, and it's something that we'll work with again in the next video. But what's left over is h bar ds dt is approximately, let's see, there's both the remaining terms are negative, so we have a minus. One of the terms is the chemical potential, and then the other is 1/2 m4 Vs squared. That looks like a kinetic energy, right? And we know that well, in fact, it's the kinetic energy of a single particle in the condensate. And we know that the chemical potential mu was interpreted as the potential energy per particle. And so what we have is the potential energy plus the kinetic energy per particle of the condensate is equal to this time derivative of the phase factor in our wave function. I'll just make one more comment, and then that's where we'll end for today. So this equation will be, well, this will be the equation that describes the hydrodynamics or fluid dynamics, /fluid dynamics of the superfluid. This is an energy expression the gradient will lead to a force equation or an equation of motion, like a F equals ma type equation. Right, so you remember, I guess, at least that, so let's see, work, which is an energy, is equal to the line integral of a force. So if you do that in the opposite direction, you take a spatial derivative of the work, then you get the force back. And so that's what we're going to do. We have an energy equation. We'll take a spatial derivative in the form of a gradient, and we'll work out an equation of motion. All right, thank you very much. That's where I'm going to stop for today, and we will pick it up from here next time.